wine and cheese later. We will also have some apple with honey, so please feel free to help us make this year sweeter than the last. At least it's not a high bar, okay? Okay, so hello everyone. This is a picture of the 3 black gem telescopes, which are currently conducting, among other things, a transient survey in the southern hemisphere. So as you see, we have one telescope for stars being disrupted, one for destroyed, and one for coalesced. Okay, and also as you see, one of the telescopes is not working. The dome is not opening, and also this translates into the fact that this was a very ambitious plan for a talk. Okay, it was too ambitious, so I'm actually not going to talk about coalescing binary stars at all. I'm sorry. I won't have time to talk about that, but I'm here tomorrow, and if you want to talk about merging neutron stars and gravitational wave follow-up, please feel free to talk to me. But also, you don't have to worry, because I found out that if you drive 15 minutes down the street, you can find the GW supermarket, which I didn't go inside, but I'm sure you can just buy your favorite gravitational wave event there. So you're very privileged to have this here near Caltech. Most of us, we wait for triggers from gravitational wave detectors, so we can't just, so we're still waiting. Okay, so no gravitational wave today, but I will talk about tidal disruption events and massive stars exploding. The reason, by the way, that my research group, we study these 3 very different events physically in their physical nature, is that they can teach us together a lot of interesting physics and astrophysics. They're connected to a lot of different processes, and I hope to convey some of that today. Okay, so we're going to start with tidal disruption events. And the story here starts, okay, part of the story here starts, my part of the story starts in 2014, 10 years ago now, where we discovered a new class of transients following, the first event was found by Suvi Ghazari in 2012. And then we found the class, and this is what the class looks like today. There are several tens of events. These are luminous transients, all occurring in galaxy centers. Most of them are quite luminous, but there's also a tail into the faint end and faster evolving. Their spectra are all very blue. And on top of this blue continuum, they have these features of broad hydrogen and broad helium, too, which is not something we'd seen in any supernova before. So the main interpretation of these events is that there's a disruption of a star by a supermassive black hole. So when a star gets close to a supermassive black hole, and this is designated by this tidal radius, RT, this is the radius at which the tidal forces from the black hole are stronger than the forces binding the star together, so the star gets disrupted. Part of the star will then accrete onto the black hole, and supposedly we will see a flare. Now, this is one of the few things in astrophysics that was predicted before it was seen. Among other people, by the main seminal paper in this topic by Martin Rees from 1988 is still our gospel today. It's still relevant today. And I'll say that these events are very rare. Just to give you a sense, this is about 1 to a few percent the supernova rate. Okay, so 1 tidal disruption event for every 100 supernovae or so in a galaxy. And for this to happen, of course, you need the star's orbit to put it inside the tidal radius. So we need the closest approach, the pericenter radius, to be smaller than the tidal radius. This is quantified by this parameter beta. So you want it to be greater than 1. Although we might get something happening also if it's outside the tidal radius, and I'll talk about that a bit later. And the other thing, the other relevant scale here is you want it to be outside the event horizon for you to see something happen. Okay, otherwise it's just swallowed whole and you don't see anything. So you want your pericenter radius to be outside of this, and this gives you a constraint on the maximal mass of the black hole that can disrupt a star and you will see it. And for a solar type star, this is about 10 to the 8 solar masses. You can push it up a bit if the black hole is spinning, but remember this number 10 to the 8, okay? We'll come back to it a bit later. So this is the evolution of our picture of TDEs from 1988, Martin Rees paper, and you see there the star is coming in a parabolic orbit. Half of it is unbound, receives positive energy and leaves the system, and half returns to the black hole. And then the idea being it somehow circularizes, accretes, and we should see a flare. More modern simulations you see here on the right from 10 years ago and from this year is a very complicated problem to simulate numerically because of the very different scales involved. So the simulations always have to compromise on what kind of components they include or not, but you can see it's a very messy problem. Okay, so the question is, what can we see? What will emit light? And the first naive picture, as I said, was the material coming back has to somehow lose energy in order to circularize around the black hole, form an accretion disk. This accretion disk will emit X-rays. We should see those. And I should say there have been several classes of X-ray transients that are attributed to this, an accretion disk form by a star being disrupted. However, the class of events I showed you before look nothing like this. They are in the centers of galaxies. Their luminosity declines at this canonical t to the -5/3, which is the rate that the mass returns to the black hole. But they're supposed to be X-ray luminous. They're optical in UV. They're tidal. Their black body radius is 2 orders of magnitude larger than a typical tidal radius where the star is disrupted. And even if you don't care about how the energy is emitted, just the total energy that is emitted is about 2 orders of magnitude less than what is expected if you just throw a solar mass star into a black hole at 10% efficiency. So this has also been called the missing energy problem in TDEs. Other kind of observational properties that don't fit. The temperature is supposed to be evolved, but these events show constant temperature over time. And a third of them show no hydrogen. And that doesn't make sense because the star should have hydrogen in it that it's disrupted when it's disrupted. Okay. So this is the main puzzle today in this field is why do these events emit the way they do? Why do they look like optical and UV transients? And people have been coming up with various solutions to this problem. The first one is, okay, you do get an accretion disk. It does emit X-rays, but it's a messy problem. There's material around. This material is optically thick. It reprocesses the X-rays into the optical. And this is why you see larger black body radii, lower temperatures. And these models on the right here show that if the reprocessing material has a smaller radius, all the hydrogen will be ionized and you won't see hydrogen lines. If the reprocessing material is more extended, you can get into radii where the hydrogen is neutral and you see hydrogen lines. So this actually predicted that you would see stronger hydrogen for larger reprocessing material. And that was in 2016. 8 years later, when we have a sample of these events, we finally see that this correlation kind of happens. So this is the black body radius on the x-axis and the luminosity in H alpha on the y-axis. And you see that there's kind of a correlation as predicted. Larger emitting areas have stronger hydrogen, and if they're smaller, they have weaker hydrogen or none at all. Okay, so this is the reprocessing picture, and you can take it a step further and say that the reprocessing material is not necessarily spherically symmetric. And so if you're looking from one side, you'll see this emission reprocessed into the optical. If you're looking from another side, you could see directly into the accretion disk, and this is where you would see the X-ray events that we see. Okay, so this looks like a really nice picture. Except there's a competing interpretation. And the competing interpretation says, okay, here's a simulation of one of the early simulations. The star just got disrupted there. Half of it is being ejected. Half of it is bound and is coming back to pass around the black hole a second time. Okay, so here it is coming back. It's passing around the black hole. You see that at pericenter it gets squeezed. I'm going to stop it just here. At pericenter, it gets squeezed, and there's supposed to form a nozzle shock here. And the idea was that this nozzle shock dissipates energy, and then the material coming back will just circularize and form an accretion disk. But in numerical simulations, this wasn't apparent. So not enough energy is being dissipated here, and the material does not circularize. Sorry. Let's see that again. The material does not circularize and instead just stays in an orbit around the black hole and doesn't form an accretion disk. Except when you add GR precession to the problem, every orbit, the material precesses a little bit, and so it'll run into the stuff coming in from the previous orbit. So you're about to see that happen over here. So not at pericenter where people thought, but actually at apocenter. You're getting these shocks from the material because of GR precession, shocking into itself, coming in from the previous round. And you get these shocks over here. And if you calculate the energy dissipation from there, you actually get the temperatures that we see in the optical events. This also would explain the large radii that we see. And it also tells you what is the mechanism by which the material loses energy and will eventually maybe accrete onto the black hole. So this is a completely different picture. We're not seeing accretion at all. We're seeing the process of losing energy before the accretion happens. And obviously, if we want to use these events to study black holes, measure their mass, measure their spin, it's really important for us to understand which one of these pictures is correct. These are state-of-the-art simulations from here at Caltech, Xiao Shan's work. And you see these stream collisions there. And here in these simulations, they cause very strong outflows in addition to probably supplying the dominant emission source, at least before peak. And then these outflows can later be what creates the reprocessing material that reprocesses the X-ray emission later. So it could also be that the two mechanisms are working at two different timescales. These are also new simulations out of Jerusalem. You're seeing here the star being disrupted, but on the right panel, look at different times. On the right panel, you're seeing where the energy dissipation is happening. And in these simulations, actually, which are claiming to be more accurate than previous ones, you do see energy dissipating at the nozzle shock. It's not enough to fully circularize the material, but it's enough to start the circularization process, and then you get this kind of cascade of energy dissipation where the streams start to form an accretion disk, and then the streams coming in later collide with that accretion disk and lose more and more energy. So this is known as the stream disk shock. So instead of the streams colliding at apocenter way out here, it's kind of an hybrid picture where you start to form an accretion disk, and the streams start to collide with this accretion disk, and this loses more energy, and you get more of an accretion disk, and so on. And you get this, you get the TD eventually. So here the emission would be really a combination of all these sources. One observational prediction of this is that this nozzle shock here should dissipate enough energy that you should see a flare in the X-rays before the main optical flare that's coming later. Of course, it's very hard to find an X-ray flare preceding an optical flare when most of the X-ray facilities are follow-up facilities. But once eROSITA came online, there was this event which indeed had an X-ray flare here a couple of weeks before the optical peak. And so this is one case. It would be interesting to know if this is common in TDs, where we always have that X-ray flare at the beginning. That could be an indication that indeed we're dissipating energy here at the nozzle shock. And that is what is helping with the circularization. eROSITA, unfortunately, is not providing that much more data now, but maybe Einstein probe could find more of these. Okay, so now we had the problem of why are these things bright in the optical and UV. We now have three different solutions to this problem, and the question is which one is correct. So either it's reprocessing material from an accretion disk, it's these outer shocks, or it's these disk stream shocks. And this has implications for how we interpret the emission and get the physical parameters and learn about the system, which is what we want to do eventually. So we're trying to constrain this observationally. This is one tidal disruption event studied by a graduate student of mine, Sarah Faris. I think this is maybe one of the best observed TDs to date. So you see that we kind of by accident got very high cadence observations of it, because everyone said, well, TDs evolve very smoothly. There's no point in observing them every day. We did. And then we see these subtle changes on the rise slope, and we see the structure on the rise. It's very subtle, but it's there. It's significant. And so this could be telling us the fact that the light curve isn't smooth, that it's maybe not just one very clean, spherically symmetric emitting region, but that there's other processes going on, and we might be seeing a combination of emission mechanisms. You'll also notice these lines up here at the top, which is where we have spectra of this event. So these are some of the earliest optical spectra of a TD. And what we can do is measure the H alpha brightness, for example, with time. And the interesting thing we found here is in the H alpha starts at the rest wavelength and then rapidly blue shifts and then slowly returns to the rest wavelength. These are other events. None of them was caught as early, so we don't know if this is a common thing or not. We want to find more of them early enough, but this is also some hint at the dynamics of the problem. Now, Sarah was criticized for this work saying, well, this is very subtle. You can't really read a lot into these tiny little wiggles in the light curve. You need a magnifying glass to see them. So she went and found the first TD in black gem, and it looks like this. And so here we have a very structured light curve and also post-peak bumps, right? The pre-peak stuff, you could say this is the formation of the accretion disk. It's the formation of the streams, but post-peak bumps, no one had any prediction that this should happen. And she's now found another one that shows this kind of thing. So we're starting to find that these things are much more variable than we thought before. And it's not all events show this. Maybe it's a viewing angle effect. Maybe it's something about the parameters of the disruption. We have no interpretation for this yet. So anyone, if you have any ideas, please let us know. Okay, and that is actually her next to the Black Gem telescope, who discovered this TDE. Okay, so this puzzle about why TDEs emit in the optical light, and maybe it's a combination of different processes going on, and also this is why it's been such a complicated problem for the last 10 years. Another interesting puzzle that I will just mention, but I have no time to talk about, is the host galaxies of these events. So this is a phase space of galaxies. The x-axis is H delta absorption of the host galaxy. This is H alpha emission of the host galaxy. So you have all the star, and all of these gray things are SDSS galaxies. So you have star-forming galaxies up here with a lot of H alpha emission, and then they go down, and these are dead galaxies with no star formation. But you have this spur here on the bottom right, which is galaxies that have no ongoing star formation. Okay, they have no H alpha emission, but they have a very deep H delta absorption, which tells you that there used to be star formation a few 100 billion years ago in these galaxies. So these are known as post-starburst galaxies. They went through some very vigorous epoch of star formation a few 100 billion years ago, 100 million years ago. And now this is where all the TDEs are. Okay, there's this one outlier here, which was found using a completely different method that targeted these types of galaxies. But most of the events, there's an incredible overabundance. The further you go out in this spur, the more dilute it is, but you still see TDEs there. So like on the corner over here, it's 100 times more, TDEs are 100 times more common than these galaxies, than they should be in these galaxies. Here, they're about a few tens times more common. And so something happens in these galaxies that a few 100 million years after they have a starburst, suddenly they're having a lot of tidal disruption events. And this is the data from 2016. There's updated from 2020, and it's still, there's a very high preference for these types of galaxies. And at least it cannot be entirely explained by observational bias. Some of it, at least, is intrinsic preference of these events for these galaxies, and we still don't know why. We have several ideas. Again, happy to talk about it later if you want. None of them work so far. So this is another big puzzle in the field. Why do these events prefer post-starburst galaxies? Now, regardless of why they prefer them, we've now been observing TDEs for 10 years. We've had several dozen events. There is now a non-negligible probability that you'll see two TDEs in the same galaxy separated by a few years. And Jean here has done a systematic search for this kind of thing and has found this event that had two flares separated by 2.5 years. The flares are quite different from each other. The spectrum of one of them, the spectrum of the second one looks a lot like TDE, this broad hydrogen, broad helium 2. This is a classical TDE. Unfortunately, there's no spectrum of the first one. So these could be two unrelated TDEs that, by chance, because these galaxies, this one is really close to the far bottom right corner of the plot I showed you before. So it's one of these TDE factories. Or it could be the same event that got disrupted twice. How can the same star get disrupted twice? Well, remember that beta parameter. If you don't quite make it to the tidal radius, supposedly nothing should happen. But stars are not uniform density spheres. The tidal radius is just for the average density of the star. Outside the tidal radius, still part of the star could get disrupted. So this is what's known as a partial disruption, right? The black hole could strip away the envelope or part of the envelope of the star, and the core could survive to come back again and get partially disrupted again. So could we be seeing a partial disruption? It's hard to say in this case, but we have another case where the two flares were nearly identical. They're separated by 700 days. You're seeing the one flare in filled symbols and the other flare 700 days later superimposed in empty symbols. So they kind of differ in the UV, but they're very similar in the optical in terms of the timescales and peak luminosity. They haven't been shifted with respect to each other. These are the real luminosities. And strikingly, their spectra of both flares are identical. This is the blue and the black spectra over here of the around peak of the first flare and around peak of the second flare compared to other TDEs. And so you see, for example, TDEs, as I mentioned, some of them have no hydrogen, some of them have strong hydrogen, some of them have intermediate hydrogen. This has exactly this level of hydrogen in both consecutive flares. And everything else looks very similar. And this is in a galaxy that's less post-starburst. So specifically for this galaxy, the chance of two unrelated TDEs within 2 years of each other is very low. So we think this is the same star that got disrupted at least twice. The third disruption, if it happens 700 days after the second, should be in early 2026. So we're waiting to see if that happens. But right now, there are two options. Okay, so either the first disruption was a partial disruption, and then the second time around it got fully disrupted and we'll see nothing in 2026, or they were both partial disruptions and it'll happen again in 2026. Okay, so here you see the bolometric luminosity of the two flares. They're slightly different in their decline rate, but the total energy of both flares is very similar, and it's very similar to the population of TDs, kind of on the low end, but it's not very low. Okay, this is the total energies we see. I mentioned that are, this inverse energy problems. TDs should be 100 times more luminous, but they're not. These are no exception. These are simulations of the two scenarios, either two partial events, and then the third one is this dashed line that we expect, or that the second disruption was a full disruption. We'll know in 2026 if it happens again or not. But either way, I think this is super interesting because there are two options here. Either these are both partial disruptions, and they look exactly like every other event in this class, meaning maybe they're all partial disruptions, and we were simulating the completely wrong problem for 10 years to try and understand it. This would also explain why they're 100 times, where's the missing energy? You're just not disrupting the whole star. Except this was the first one that was on a 2-year orbit that we could see, and the other ones, who knows, they might come back in 10 years or more. Okay, that's one option. The other option is the second, if we don't see it happen again, the second event was the full disruption. And now your problem is partial disruptions and full disruptions look almost the same. So our class is actually a mix of partial disruptions and full disruptions. And how can they look the same? Either you disrupt part of the star or all of the star. How do you get the same total energy even? Okay, let alone all the other properties. So I think this is going to be a very interesting event, whether it happens again or not. And we're going to have to refine how we think about these optical TDs. So could they all be partial disruptions? Or is it a mixed bag with things that look very similar to each other observationally? Okay, so you can now say, well, given all these puzzles, why are these TDEs? Right, maybe the solution is they're not TDEs. There's something else. There's some other type of transient. Okay, so I think the best answer to this is looking at the rates of these events as a function of the black hole mass of the galaxy in which they happen. So this is early work by Schroed-Van-Vensen here on the left, and then work done here at Caltech also more recently, confirming this result. So you're seeing the rate of TDEs as a function of black hole mass, and you're seeing a very sharp drop at 10 to the 8 solar masses. And if you remember, that's the mass at which beyond it, the star gets swallowed whole by the black hole and you shouldn't see anything. And this is exactly what we see. Okay, it's evidence for event horizon in these black holes. Right, if these were supernovae or some other accretion-related transient, they wouldn't care about this number, 10 to the 8, like TDEs do. Okay, and this is seen also with larger samples, this drop at 10 to the 8, which drops faster than the mass function of black holes. Okay, so I think this is very strong evidence that at least as a class, what we're seeing are indeed tidal disruption events, and so it's really important that we solve these puzzles if we want to use these events to understand black holes better, their formation, and also accretion processes, and also the dynamics of these post-starburst galaxies about why are they driving the TDE rate so high? What's going on in the centers of these galaxies that is causing this? Okay, but regardless of all these puzzles, which we're trying to solve, you can also use TDEs to study the environments of supermassive black holes. This is work by graduate student Megan Newsom in Santa Barbara, whom I'm working with. And so she's doing this in two ways. Here's the tidal disruption event light curve where she found this infrared bump at late times, near infrared. And this is interpreted as a dust echo. So the TD goes off, it heats the dust around it, and then the dust emits infrared with a time delay based on its distance. So you can actually map the dust at parsec scales around supermassive black holes by this method. This is not the only case. And the second way you can do it is with these events with very high ionization emission lines. These are known as corona lines, nothing to do with the black hole corona. It's just the name because they were first discovered in the solar corona. Very high ionization lines. You see these things happen in galaxies. Suddenly these high ionization lines go up and down. And we caught the second ever case where this was seen to happen together with a TDE. So you had a TDE, and then you have these ionization lines go up and down. This is a light echo of the emission from the TDE on material that's around the black hole. And you can again start mapping the environment of the supermassive black hole this way as well. Okay, so this is very interesting. And all of this is just the tip of the supermassive black hole transient iceberg. There are other classes that we are finding of transients around supermassive black holes. Yes. These are transient lines. Okay, you can see them changing within weeks, and then they disappear. Okay, so these are supposedly coming from very highly material that was around the black hole that was ionized by the flare of the TDE, and is then, emitting these lines. Yeah, okay, it's not coming from the same place. Yeah, okay, I agree. This is mapping exactly what's coming from where is interesting. It could be that the H alpha is part of this reprocessing material, and the high ionization lines are exposed directly to the accretion disk from a different direction. So this class I showed you is just one of many. These are the events up here. A couple years ago, we discovered a new class. The spectral lines are much narrower, and the types of lines that they show are known as Bowen fluorescence lines. This was a predicted cascade of lines that's supposed to happen around black holes, predicted in the 80s. This is the first time we saw it. So we call them Bowen fluorescence flares, or BFFs. We've seen a few of these now. They seem to prefer AGN. So these are flares that happened in pre-existing AGN. So we think this might be related to a pre-existing AGN disk, either having some instability and producing a flare, or a star coming in and disrupting the disk temporarily and producing these flares. Another case, and this we've only seen one of, is a flare that happened in parallel to an AGN changing its type. This was a narrow line AGN. This flare happened, and then it's a broad line AGN, and we see this process happening. The broad lines developed over months, so that already killed a few theories about changing state AGNs that required longer time scales. In parallel to the optical flare, the X-ray went down and up. These are the lines getting broader. Very puzzling event that is still continuing to produce puzzles to this day. So again, this landscape of transients around supermassive black holes is, I think we're just starting to explore it. The challenge here is they're hard to find. Okay, so this is a master project by a student, Iair Arcavi, who looked at what happens if you classify everything in a galaxy center that goes off. Well, I told you TDs are about a few percent of supernova rate. This is what you get. TDs are about 2% of what you get. The rest are supernovae, most of them type 1a. These Bowen fluorescence flares are even more rare. Okay, so TDs are blue, whereas supernovae become redder with time. So you can filter at blue at early time, and that kind of helps you, gives you a little bit more fraction of observed TDs. And you can go to the post-starburst galaxies where the TDs really like to be, and there, it's starting to be a significant fraction. But this is very small numbers. There are very small numbers of these galaxies that we know of. So it's not a great strategy if you want to find a lot of events. So if you want to find TDs, you need to devote a lot of spectroscopy time, which we are planning to do with the new spectrograph coming online next year, Son of X Shooter, SOX. This will be on a 3.5 meter telescope in La Silla in Chile. But I think the real revolution is going to come in a few years when we launch Ultrasat. Ultrasat's a 200 square degree UV imager in space. So it'll be the first wide field transient survey in the UV. These things are very bright in the UV, so it should find thousands of TDEs, hundreds to thousands per year out to very high redshifts. So it'll be very much easier to find them. And we could even start probing the redshift evolution with ultrasat. Okay, so I think exciting days ahead for transients around supermassive black holes. Okay, I'm going to shift gears now to talk about core collapse supernovae and their progenitors. Again, can teach us a lot of interesting physics and astrophysics. And the main question in this field is, how do these stars explode? This is still an open question. And the reason is that it involves a lot of complicated physics. This is just part of it. But one thing we can help constrain observationally are the conditions of the progenitors before they explode. And this provides starting conditions for the simulations of the explosions. They provide boundary conditions for evolution of massive stars. So we can try and do that. Okay, so this is the puzzle we're dealing with here, is which stars explode as which supernovae. One way you can do it is you can wait for a supernova to happen in a galaxy where you have pre-explosion HST images, which actually identify the star before the explosion. This is work from the good old PTF days. This was the first of this type of supernova where we found a progenitor star. And you can see the star directly, okay? And what you do is you see the star in various filters. You fit the SED of the star to a model massive star spectrum. And then you say, okay, you put it on an HR diagram. And you say, which stellar evolutionary track from my favorite model goes through this star? And if it's this one, you say it was a 13 solar mass progenitor, okay? And this has been done for a few dozen cases. Okay, but then Schuyler Van Dyke comes along and says, no, that's completely wrong. It's a 15 solar mass progenitor because you didn't take into account the reddening and the distance correctly. Okay, and this is obviously very sensitive to those kinds of things, and it can skew your result a lot. So we thought, okay, why not do this systematically? Okay, so another master student project by Tomer Katz took the grid of missed massive star models from MESA, and said, okay, if you have different priors on the IMF, on the distance, on the extinction, on what metallicity this star is, actually, that would influence your result, you would get different posterior distributions, right? The mass is not 13 or 15, it's a posterior distribution depending on what you assume of the, in the environment of the star and everything in this system. So you can actually also use this to figure out, okay, if I change my extinction and distance assumption, how sensitive is my progenitor estimate to these parameters? How sensitive are my errors to the errors in photometry? How sensitive are they to the wavelength coverage? Like, what's the best wavelength coverage I need to best constrain the progenitor star? Okay, and then you run this. This is on a star that was calculated. So these lines were published parameters for these stars. So we reproduce that. But now it's not just a number, we have a posterior distribution, and we can see how it's changed, how it changes when you change your assumptions on the metallicity, on the distance, and everything. Okay, so we're about to release this software, and you can run it on your favorite progenitor star and see what you get. And Tomer has asked me the students are currently arguing what to call this. Okay, so the two runner-ups are the progenitator or progenit. Okay, so if you have strong feelings, what we should call this, please let me know. Okay, I promised them I would ask. Okay, the problem, even if you do this systematically, is that only a few dozen supernovae have had their progenitors imaged. So it's not going to give you very large number statistics. One solution to this is actually, forget about the progenitor star, just catch the supernova early. And if you catch the supernova early, which you can do for many more cases, you can infer actually a lot more about the star. Its size, its inner density profile, and the mass loss history before it exploded. I am a bit short on time, so I'm going to skip how you do this. In some cases, I'm going to tell you just one of the methods. The most common type of supernova in nature is a single red supergiant exploding as what we call a type 2p supernova. And here you're seeing light curves of one of these type 2p's. And you're seeing models of these light curves. Now, the regular models are these dashed lines, which do not fit the data. And in every single case that these people looked at in these papers, they had to add something at the early times to fit the data. And this something is interaction with circumstellar material that is confined around the star. So there's other evidence for this, but this is one of the main evidence that the early light curve of the supernova, you have to add this circumstellar material that the supernova runs into in the first few days in order to fit the luminosity of every single supernova we've seen. Right? If you wouldn't have that, the supernova, you would see it rise kind of slowly on a 10-day time scale at the beginning, kind of like this one. Okay, so this is graduate student Sondos Mohsen, who found a type 2P that rose very slowly at the beginning, and we thought maybe this is the rare case where a star literally exploded in a vacuum with no interaction. Okay, so she fitted this with shock cooling models, which is the early emission of supernovae, and actually when they never fit the models before, because they had this added interaction, this one fits pretty well. We have this other new tool where we can fit numerical light curves of supernovae to the data. And one case, we told it there's no CSM, no circumstellar material, and found a nice fit. And the next case, we told it, okay, you're given 2 more free parameters of the circumstellar material, basically how much there is and to what extent it goes out. And the fits basically said, no, thank you. I don't need these 2 extra parameters. Here we're seeing with and without CSM, and the thing to look here is the radius. You give it a free parameter, tell me how much CSM you want, and it tells you 0. I've never seen a model say, I don't want extra parameters. Okay, but this one was really insisting that the supernova had no circumstellar material. This fitting software is called SNEMC. That's settled. I've settled it. It's a new tool that takes numerical models of massive stars and explosions and allows you to do these kinds of fits. Is worked by 2 other graduate students in the group, and we'll get to them in a second. Okay, but why do we care? Why does it matter that we found one supernova that showed no interaction? Okay, fine. There's a rare case. This is interesting because sometimes it's the rare cases that teach us about the population. This supernova that had no interaction is also the lowest temperature supernova we've ever seen of this type. This is temperature of a sample of 2P supernova versus this one, and the highest velocity one that we've seen. There's actually a shaded region here. Believe me, there is a shaded region here. This is a sample of 2P supernovae, and this is like 2 sigma out in terms of its velocities. So is this just a coincidence that the one event with no CSM interaction has the lowest temperatures and highest velocities? Or is there some physics going on here that connects these 2 things that we don't understand? Okay, the CSM is at the very early, it's supposed to affect only the very early emission. It's not supposed to affect the whole supernova. So what is going on? So we want to find more of these in order to answer that question, and also under the question of, how many red supergiants experience this kind of mass loss before exploding, how common that is. Okay, to do that ultrasat's going to be great for that as well, because it'll find the UV flash at the shock breakout, which is the first light emitted by a supernova. We have other surveys we're involved in. Again, talk to me if you're interested about that, because I want to use my last 5 minutes to talk about the thing that is relevant to all 3 of these, that we're actually probably not going to solve any of these problems if we don't understand better, and that is stars. Okay. So stars are the culprit here, okay? And if we want to understand how stars die, maybe we should take a closer look at how they live. And it's important to say out loud that stellar evolution is not a solved field, especially for massive stars, okay? There are many unknowns there. I'll give you just one example, okay? Decades-old mystery, the Humphreys-Davidson limit. This is an HR diagram of the Large Magellanic Cloud, but it's not just there where it's seen. Why are there no stars in this top right corner? If you just do models of stellar evolutionary tracks, you should see stars in that top right corner. Okay, and work by former postdoc of mine, Avishai Gilkis, showed that if you want to reproduce this and get, avoid stars going into that corner, one thing you can do is increase this parameter called alpha overshoot. This is the core overshoot parameter. So you have a convective core in these stars, but that core doesn't just, the convection doesn't just end abruptly. There is some cells that overshoot into the radiative zone. And how much is parameterized by this parameter, okay? And what that does is mixes the material and changes the evolution of the star. Okay, so is this the solution? Do stars have that high of an overshoot parameter, or is this wrong? We don't know what the overshoot parameter really is in these stars, but we have a way to find out, and that way is asteroseismology. Okay, so stars pulsate, including massive stars. They oscillate, and these oscillations are influenced by many parameters of the star, including internal rotation, and this core overshoot parameter influences how the star pulsates. So if we can analyze the pulsations of the star, we can reverse engineer its internal parameters and, learn a lot more about what's going on. So this, however, is very challenging observationally. This is the first time it was done in 2003. These are the 6 top frequencies that the star is oscillating. Okay, so a few things to notice here. It's about 6 cycles per day, so it's like a 4-hour period. Okay, so you need to sample on hour timescales to see this, but you get these very nearby oscillation modes, nearby in frequency, which causes beat patterns on timescales of months. So you need to sample it on timescales of months, but if you can do it, that's great. You measure the overshoot parameter, and it is not as high as Avishai needs for his models, at least for this one star. But this took 21 years of observations, okay, from a single site. That is not scalable to a sample, okay? So we found a way to do this in 17 weeks instead of 21 years. Here's the key. This is a simulation of the oscillations of the star over a few, these 17 weeks. And it turns out that if you can sample it for 48 hours once a week, you get the same kind of data that they got by sampling it on classical nights. They were limited by single site observations, which took them 21 years. So you can actually reproduce the exact same frequency spectrum in 17 weeks instead of 21 years. The key is you need to do continuous observations for more than a night. Okay, so one way to do it is from space, and the TESS Space Telescope does this fantastic, but for the full astroseismic analysis, to get these parameters, you need colors. You need to know the oscillation spectrum in various colors. Only then can you identify the modes, and only then can you use the models to constrain the parameters. So TESS doesn't give you the colors, okay? So you have to do the colors. So this is why we have to do it from the ground, and the same network of robotic telescopes that we used to follow transients at early times, we are now using to do these 48-hour observations around the globe of massive stars once a week in order to do a sample, okay? So we tried this, it works. Here are the oscillations of a few stars. Each color here is a different site on the planet. You'll notice this is 48 hours. So you can see the oscillations across the different sites. And this was just one set of 48 hours, but if you repeat this every week, you'll get the full oscillation pattern. And curiously, we did this for that star from 2003, where we know the answer, and it sits right on the predicted light curve from 2003. So this is telling us these oscillations are also very stable on decades timescales. But we want to test this further, also how stable these oscillations are. Okay, so we're doing this project over 3 years. Here's our first star that we got multiple runs of. So we do use the test data to fine-tune our observing strategy to these frequencies of this star. Once we do that, we get the frequencies in multiple bands. We can do the full astroseismic modeling. We can measure the internal parameters. The goal is to do this for 20 stars. So far, 9 massive stars have ever been studied fully with asteroseismology. We want to triple that sample in 3 years using this method. Okay, so I am out of time. I know that was a lot. So I will summarize it very briefly. We talked about tidal disruption events, where some of the main puzzles are what is the emission mechanism and why the post-starburst preference. There are a few other puzzles I didn't go into. And we're finding new repeating events. We're finding bumpy events. We're mapping the evolution of the spectra at early times. We're mapping the environments of supermassive black holes with these events. And we hope these constraints will help solve some of these puzzles. We talked then about massive stars and their explosion. The main puzzle here is which stars explode as which supernovae, and what happens to massive stars right before explosion. And we're trying to tackle that with looking directly at progenitor stars before they explode, constraining them through other methods, including their pre-supernova mass loss, and using astroseismology to try and constrain these stars directly while they're on the main sequence, so well before they explode, to try and understand them better, okay? But stuff I didn't have time to talk to and talk about, and you're welcome to talk to me about if you're interested, gravitational wave follow-up. These surveys we're using, BlackGem, LaCia, LS4, SOX, Ultrasat, the tools we're building. Feel free to talk to me about any of that. I'll be here tomorrow, so thank you very much, and Happy Jewish New Year. Question? Maybe Monty first?
Oh, sure. So the correlation with the close star galaxy.
Yes.
That's natural that perhaps they have a big population.
Yes. That is an excellent idea because I also had it. But it turns out that the timescales for disrupting a giant star are much longer than the timescales we see in these events. So because the tidal radius is much larger, the disruption happens at a much larger radius, and the timescale is supposed to be longer than the weeks to months that we see for these events. So we don't think these are giant stars being disrupted, but I don't, maybe the idea is not, it's still worth exploring for sure.
There are many events now for which sometimes you see the flash ionization features, sometimes you don't, sometimes they persist for many days. Fraction of population.
Yes, okay, so I'll explain this in a second because I had to skip this. This flash ionization features are a different way of probing the CSM around massive stars before they explode. Is you take a spectrum very quickly after the supernova, you see these very high ionization emission lines that disappear within days. And the interpretation is this is very confined circumstellar material that the supernova then runs into and wipes out. But you have this window of a few days where it's illuminated from inside, and you can kind of map the CSM and even get its composition, right? So this is a really good method, and indeed, many stars show this and many don't. But the CSM that we're probing with the early light curve is different than the one you get from the flash ionization. It's at a different position. It's a different radius. So it's not the same CSM that the flash ionization lines probe. But it would be interesting to see the connection, I agree. Because for this event where we know there was no CSM from the light curve, we don't have early enough spectra to say if there was or wasn't a flash ionized CSM, but that doesn't contradict because these are two regimes of CSM that are separate. So it's true that what we're saying is only about the regime probed by the early light curve, not what is probed by flash spectroscopy, was definitely a complementary method. Yes. No, yeah, it's a funny thing that, we used to consider these things exploding in a vacuum, all of them. And then suddenly, now all of them actually explode in CSM, and the weird ones are the ones that explode in a vacuum.
Yeah. So the rate limiting step in tidal disruption events can be one of two, of course, can be both, but one star, has to be perturbed or orbit be fed into a black hole. And so the other one is to have more stars in the center, which but it's not clear to me that the second one is more important. Lifetime potential of our star. So it might be that these stars are exploding. That's where the peak explodes. And the only way this makes sense is you remove or rearrange a large amount of gas in the center that you actually change the gravitational potential. Not in a big way, but enough to start perturbing the stars that they're slightly more random.
So you're saying the disrupted stars are these 10 solar mass stars at the end of it? No, they're providing the gas.
Change the gravitational
potential.
Get orbits slightly chaotic so that
Yeah, absolutely. And this is actually one of the leading ideas is that these things don't have spherically symmetric potentials in the core. Nick Stone has done a lot of analytical work on this and also simulations. This could boost the TD rate. And we're trying to constrain this observationally by looking at the morphology of these hosts at very high resolution. So yeah, this is definitely one of the possible solutions, the aspherical potential at the center, and can definitely do that. The other thing you mentioned is that you have more stars and you're not sure that's a dominant factor. That's a very good intuition tree, because we used to think that, yeah, these things also have very cuspy cores. So you do have more stars at the center. So we thought that was the solution, but it turns out, in this recent work coming out of the Technion in Israel, that if you have more stars, you're actually shooting yourself in the leg, because you get strong interactions between the stars, and that actually throws out more stars than it throws in. And so you actually have to explain why you get this overabundance despite having more stars in the centers of these galaxies. So yeah, that's become another problem. So it might be the potential that's driving it. Yeah. Yeah, no. Let me bring it up. Unfortunately, they are not. I should say it's not the first transient with a bumpy light curve, but it's the first tidal disruption event with a bumpy light curve of this class of tidal disruption events. But yeah, you see that the time actually seems to get longer, at least between these. Maybe this is 1, 2, 3, 4, 5 bumps. It's not quite, yeah, it's not quite periodic. But yeah, if you have any ideas how it can get longer, I'm very happy to hear.
Then you have the opposite problem that you have a much lower rate of 50 particle events to not get any much lower rate. We need to explain why in the late stars or galaxies preferential particles disrupt.
Yes, yes. I agree. You now have this problem. And also, where are the full disruptions? Right? Are they the X-ray events? Are they something else that we haven't yet identified? I agree. It's very troubling that if these are all partial disruptions, it does solve the missing energy problem, but yeah, it creates these other ones. Yeah, yeah, definitely could be. Hoping maybe Einstein probe starts finding them. Yeah. Right, right. This host galaxy preference is strongest for these optical events. The X-ray events don't seem to strongly prefer these galaxies. Events found in the radio, events found in the infrared, they seem to be disjoint in terms of their galaxy preference. There's some commonalities, like they all seem to like Green Valley galaxies, but the post-Sternberg specifically, which is a subset of the Green Valley, is just true for the optical one. So yeah, why would partial disruptions happen preferentially there? Yeah, I don't know. Mm-hmm. Mm-hmm. Yeah, yeah. Yeah, you're right. It's not just a bump. There's an IR axis the whole time. So, the earlier the IR axis, the closer the dust has to be for it to cause it. So we think, I should say, previous events have seen an IR axis kind of very much later, right? The optical thing went up and down, nothing weird about the I band. And then a few months or years later, you see a flare in the infrared. This one is happening like convolved with the actual flare. So our interpretation, which I'm definitely not claiming is the only possible reason, is that this was just the very, very confined dust, like very on parsec scales, very near the black hole, and it's giving you this excess already around the peak of the TD itself. But again, happy to hear other ideas. One thing is, yeah, many TDs were not observed in the I band because they are very blue events. They're like 30,000 degrees. So we kind of neglected, we observed them mostly in the UV and blue colors in the optical. And I think this has now motivated us to also make sure we monitor them in the near infrared. So we don't have many cases, so we still don't know.
Sorry.
Yeah, it's okay.
Thank you, Iair, again, for a great talk.
Thank you.